Hello, dear participants. Expert will join at 6:15. We see he is busy in other meeting, so please wait. Dear participants, expert will join soon. Oh, good evening. Yes, hello, sir.
Hello, good evening. This is Gagan here.
Yes.
This is Dr. Gagan here.
Okay, okay, sir. Yes, you are audible. Okay, I will make you a presenter. Wait a second. Dear participants, today's expert is Dr. Gagan Gupta. Sir, Gagan, sir.
Yeah, I'm here. Hello.
Yes, may I audible?
Yeah, you're audible.
Okay, okay. So, dear participants, so Gagan sir, how are you?
I'm good. How are you?
Yes, I am fine. Okay. So, sir, before we start, may I give your brief introduction to our participants?
Okay, sure.
Okay. So, dear participants, today's expert is Dr. Gagan Raj Gupta. He is currently associate professor in the Department of Computer Science and Engineering at IIT Bhilai. He received his BTech degree in Computer Science and Engineering with an Institute Silver Medal for from IIT Delhi in 2005. He received MS in CS from University of Wisconsin in 2006 and PhD in Electronics and Communication Engineering from Purdue University in 2009. Then he spent 10 years at AT&T Lab, USA, and the lead architect for a new technology development in monitoring and probing AT&T mobility using 3G, 4G, 5G, and IMS physical and virtual network function. His current research interests include ML system, that is basically generative AI for telecom networks, distributed GNN, federated learning, split learning, failure prediction, and root cause analysis, medical devices, and high dimensional data analysis. So enjoy the session, dear participant. So, sir, over to you. I think you can share the PPT. Yes.
Okay. So we're going to talk about split learning today. Split learning is a type of federated learning. So I'll be giving some background first about what is federated learning. We'll be looking at some works in split learning. Then I'll be telling you about a type of split learning, efficient split learning that we have developed specially for the IoT devices. So this is very lightweight, this is easy to implement, and can also get very high efficiency and accuracy. So that is where we will spend most of our time. We'll show like what were the goals of the experiments that we did, our setup, various use cases. For example, we will show how it is applicable in medical imaging, and then we will conclude and provide some future work. We also have various code that is available in our GitHub repo. We have examples from federated learning. We also have some examples on split learning. So that can also be demonstrated. Like we have 2 sessions today, so combined we have a lot of time. And I'll be presenting these slides. You can ask your questions. We can go step by step. Maybe after every 5 to 10 slides, I'll ask for questions, and then it can be an interactive session. Okay, so let me start with some background first. So we all know that deep learning models, they thrive on large data sets, which means that deep learning models are just trying to understand or learning patterns in the data. And because there are a lot of parameters in these models, like why we are calling them deep is because they have a lot of layers and a lot of parameters need to be learned, and complex functions are being learned. So we need large data sets. And it is difficult to get all the samples, all the data in a single place. So, for example, if I'm building a model for MRI analysis to understand like where are the tumors in the brain, then I need lot of MRIs. And the types of problems that might be there in the whole population may not manifest in one place. So we may have to go to many hospitals, collect the MRIs, do the annotation of the data, segment the tumors, and then build a model which can like predict or segment these tumors just from the input MRI. Now, there is also this sensitive data in the healthcare, finance, and other industries. The people from whom we are taking these reports or collecting this data, they do not want their identity to be revealed, or they don't want, like their data to be used in some way that can be, used against them, or in some harmful way they don't want it. So there are concerns of data privacy in all the various different sectors. And then, so first I told you that the data is not present in a single place, it is distributed because data is generated from people or lot of, like maybe machines, maybe the vehicles, but this is all distributed. It is not at a single location. So I have to go to these so many people or so many places or so many devices to collect the data. And then I have to also respect the privacy concerns of the users to whom the data belongs or to the organizations whom this data belongs. And third thing is that we don't have that much computation, especially when we are talking about IoT devices. The IoT devices are having some sensors, maybe even some cameras, and they are getting some data, but there is lack of computation capability. I mean, there is the computation capability is limited, and I want to effectively use this computation capability that is there in my IoT devices. So this motivates that we should develop communication efficient, privacy preserving, collaborative learning on these resource constrained devices. You can call them as IoT devices, edge devices. There are like lot of different names for these. And how can we all combine our data together, combine our processing together to produce a model that works well on our data? It better than what we could do alone. So if I had some small amount of data, I could do machine learning or deep learning also. But then the accuracy that I will achieve on my own data set would be relatively lower. But when we combine the insights that are gained or models that are obtained from all of our data individually, the combined collaboratively learned model will be much more accurate. So that is what this field is all about. It combine the data, combine the insights, combine the model together and form a more efficient and more accurate model. So first I will discuss the federated learning setup. In the federated learning setup, there are two types of entities. One is the data owners, like for example, they could be phones, they could be IoT devices, as I was saying earlier. And then we have a model owner, which is the federated learning server. So it's a multi-step process. In this step one, we are doing initialization of the task. We need to know what kind of model you are trying to build. So let's say for a smartphone, we are building a face detection system. So something like this, which is detecting the face, and maybe you have to unlock your phone or something. So for that, you have set a face detection. Okay, so now a face detection model would be placed here, let's say, and now they are these clients, and clients are the data owners. So now you have to set on which faces will this phone open, like whether it's your face, your family face, your friend's face, so they can open the phone. So you will set that, and now we have got some data on which the model has to be trained. So this phone or this device will now update the model on its local data and get a local model. The local model will now be uploaded or transferred to the server in a secure way, in a secure way. And then the server will do a model aggregation. It will combine all these local models. So because the local data on each of the clients is different, their models will also be slightly different. And therefore, we are now aggregating all these models. And the fifth step, the last step, is the global model update, where we send this aggregated model or the combined model back to all these clients so they can now do their inference or further learning. So the same process may repeat again, and it will come to convergence. Basically, it will come to a point where it cannot be improved any further by such updates. So this is the framework of the federated learning. And we can say the combined global model is now being learned on a entire data set of all the clients, but none of the clients transferred their data to the server or to each other. At no stage the data left the clients, only the model updates that were learned by the clients were exchanged. Okay, so this is how it is working. Each selected client uses its own data set D of K to train a local model, uploads the trained model to the server. At the end of the training iteration, the trained models from all clients are aggregated. The above process of local training global aggregation is repeated for multiple rounds until a certain level of accuracy is achieved. So any question? So we can have a pause here now. Any question on federated learning so far? Everyone is okay with this collaborative nature of learning, the fact that data is not leaving the clients. Any question anyone wants to raise?
Participants, you can ask the question now.
In the chat also you can post it, you can unmute and
Yes, sir.
ask. So we will go slow,
So,
but we'll cover the whole material.
or it will be better after completion of the first session, you can ask the question through chat window.
No, now also it's fine.
Yes, yes, yes. It's participant's choice.
Participant choice.
Sir, when edge devices are heterogeneous,
Mhm.
will it have impact on if when the precision is different? What kind of impact you will be having on the model?
Yes, it's a good question. Heterogeneity of data. So it would have an impact. We will see it, but the short answer is that what would happen when the clients will have heterogeneous data, their model updates will also be heterogeneous, and the aggregation step becomes more complex and difficult. And also, the performance of the model after aggregation may not be very high. So there is a concept of personalized models that is used when there is heterogeneous data along with a distribution match. I mean, the training and test distribution on the client has to be the same. Then the personalization works very well, and we will discuss this. So
Sir,
heterogeneity may be
actually I'm asking about the representation of the data. When different architectures are there, then the precision could be different, right? The data itself with different precision.
that for that we'll have to do a normalization. So all of the model would be on the same precision. Okay, and because the model architecture is common to all the clients. We are not changing the model architecture. So usually we will do a data normalization at the client level, bring it to the normal form or the normal whatever standard precision our model is expecting, and then translate it back again. Does that answer your question?
Yes, sir.
The keyword is normalization. You have to normalize the data such that the data format, the data precision is same across all the clients. And it can be done locally. It doesn't need to be like done at the server. The client can normalize it on its own. So it's just a pre-processing step now. For example, one phone could be a high resolution phone. Another phone may take images in a lower resolution. So this is very common in most of the deep learning models. They work with 224 cross 224. And most of our smartphones and all, like they are taking images in very high resolution, right? I mean, even HD they are taking. So all of those pictures or photos are then converted to 224 cross 224 first, and then only they are passed into the models. So this is an example of heterogeneous, formats or even, resolutions at the client level, but the model is still being trained and updated in 224 cross 224 as the input data, input images. Can everyone relate to this example?
Sir, another questions from Riyanka.
Okay.
Can we use this stock market data prediction? This is the
So,
question.
yes. So basically, I mean, in the stock market, we have to think of what is public data and what is private data. right? I mean, if the data of the stock is all something which we already know, I mean, which is publicly also available, then what is, in which way are we having private data? That is what we have to think. If all the data is available to everyone and I mean it's public, then there is less motivation for federated learning. Motivation for federated learning comes from like, so in the stock context, if there were certain ways in which people were investing, or there are some patterns that they are following, and then we can probably have some strategies that could be learned. I mean, especially like I would think of something like reinforcement learning or some kind of a policy that you may want to learn with the help of federated learning. Not so much about the value of the stocks and how they're updating, but what are the ways in which people are investing, or basically when are they losing money, or and things like that. That is what you can learn in a more like a reinforcement learning framework along with federated learning. So federated learning has to do with locally generated data, things that you want to keep private, things that you want to, like collaboratively learn, but without sharing the data. That is the ideal scenario. When data is available on a central repository, like stock market data is available in a central pool. So then I don't think there is much of a application. Is that okay? Is that answer okay?
Yes, sir, it's okay. Please continue.
So now let's discuss the benefits and some challenges that come with the federated learning approach. First benefit, as I told, was data privacy. Also, it's a scalable architecture. We can have thousands of clients, tens of thousands, millions of clients. In fact, companies like Google, Apple, all of them are using this kind of federated learning to deploy their applications, to customize their applications, to personalize their applications. This is already being used at a large scale, especially because there are strict regulations on data privacy. So companies have to comply with the privacy regulations, and therefore they cannot collect all the user data in a central place. So, and they ask for your consent and our consent of the users that can we collect this data or not. And depending on what you choose, then only they can maintain your data. That too also for a certain retention time. So therefore, they have to inbuild some kind of data privacy layers in their machine learning architecture, which can help you sort of get a personalized experience when you use their applications. So limitations, and especially from an IoT perspective or a edge processing perspective, it requires heavy resource consumption because these deep learning models are very large. They have a lot of parameters, so they need memory. There are a lot of computations going on in the neural network, so it requires CPU as well. Then comes to this disparities in data distribution. We've just discussed that the different phones could be using different resolutions. Their formats may be different, so we need to do some normalization. There is system heterogeneity. The resources like CPU, memory available at different phones could be different. There's also a lot of communication overhead because these models need to be exchanged. At least the updates in the model needs to be exchanged, so that involves communication. Then there is system dynamism. Some clients may enter and they may leave. Someone's battery may run out of, they may run out of battery. So it may get power down while it is in the middle of these updates. And there's again some privacy and security concerns. For example, we want the models to be aggregated securely. What if there is a malicious client who can get these model updates and try to generate some attack on the system and corrupt the model, upload a false model which can corrupt other models. So there are many other scenarios which are a concern with the federated learning. So this is like uh, you know, a chart which summarizes some of these approaches that how are people trying to address this resource constraints. Okay, so like FL algorithms can handle data heterogeneity and system heterogeneity. Model aggregation, it can be improved so that it can also handle system dynamism. Client selection can also handle data heterogeneity and system heterogeneity, and it can also address constrained resources, system scalability, system dynamism. Then there are communication control methods or policies that people have implemented to reduce the communication overheads, the constraint in the resources, or system scalability issue. And privacy security protection schemes have been implemented to improve the privacy and security. Basically, an idea of like how the literature or the researchers are trying to address these questions or these problems. And split learning is also one of the approaches that people have developed to address many of these issues, which would be the main focus of our session today. So in this framework, a machine learning model or a deep learning model is split into two portions. One is at the client, the other is at the server. We saw in federated learning that it's a client server architecture. There are lots of clients and probably a single server or maybe a pool of servers for load balancing. So same thing here. In split learning, we also have a lot of clients. And now instead of keeping the model entirely at the client, we are splitting the model. A model is nothing but some sequence of computations. If we are talking about neural networks, models are just, a sequence of layers. There are some interconnections between the neurons in the layers, and the data is passed, some functions are computed, and at the end, we get some output. Okay, so same thing. We have split this full ML model. There were 5 layers or 5 blocks in it. 2 blocks are with the client, 3 blocks are with the server. So similar to federated learning, all the raw data, training data are stored on the client without being transmitted to the server. The data stays at the client only. Data doesn't leave the client. The training of the full model is performed by executing a sequence of forward propagation and back propagation between client and server. This is how neural networks are trained. The data is passed here, the activations will flow in the network. We will come to some kind of output. Based on the output, we will generate a loss, compute a loss, the gradient with respect to loss, so del L by del W. The gradient of loss with respect to the parameters will flow back, and then we will do a weight update or parameter update step and update our parameters. Then again, this process can continue. So the client uses the training data to feed the model WC, the client side model, and performs forward propagation until the cut layer. So here the cut layer is between 2 and 3. We have cut the network. Half of it or one side of it, one portion of it is with the client, other portion is with the server. The cut layers activations are then transmitted to the server. So now we are communicating the activations, which we are calling as the smashed data. The server uses the smashed data received from the clients as inputs into its model. Its part of the model is WS and completes a forward propagation on the remainder of the full model. Okay. And then after calculating the loss function, we start back propagation. Then we do the weight updation. The server transmits the gradients back to the client. The gradient are received by the client from the server. Then backpropagation happens in the client part of the model WC, and then they can also, again, the clients can update their parameters. Now, each client had its own copy of the client side model. The parameter updates are happening at the client side. They are happening independently. Every client can now have potentially its own variant of the model. The parameters at the clients would be slightly different. The server side model is now common. It is shared by all the clients. So far, any question on how we split it and how the learning happens, how neural networks are trained in a split learning mode? Any question on this?
I think, sir, no question
Okay,
from the
so
participant.
sure. Okay, so now we are moving to the various variants of split learning. There are many configurations in split learning. So far, I have described this one, A, configuration A, where there is a client server. The clients are sending the smashed data to the server. The rest of the layers are handled by the server on the server side model. Then the loss is computed with the output and the gradients flow back. Now in the B, there is an extended configuration. We can have some intermediate servers, which again can do some load balancing. This is just a layer between the client and the server. There are some intermediate servers to help with this, computations or gradient flow and stuff like that. Now comes C. C is a U-shaped configuration. Here we see that the fifth layer is also back with the client and the outputs are also with the client. In configurations A and B, the client have to give the correct outputs to the server so that the server can compute the loss function. The loss function requires both the predictions as well as the ground truth for the training data. But in configuration C, the clients need not share the labels or the ground truth with the server because the first few layers are also with the client and the last layer of the or last few layers of the model are also with the client, and it becomes like a U shape. So this is the U shape. So input comes, it goes through these two layers, then it goes to the server, it passes to these layers, the activations are then sent back to the client generates the output and the labels, the loss is computed, then the gradients are back propagated to server, and from the server they are back propagated to the clients, and the parameters are updated. And apart from this, there is also a vertical configuration. In the vertical configuration of the split learning, we'll not like discuss that too much. Part of the input data. So here, all the input data was present with the client fully, but this is a scenario where part of the data is with client 1 and part of the data is with client 2 or client 3 or so on. So that is a situation where different clients have different portions of data. I mean, even one row is not complete. It is as if, let's say in the picture example, there are three cameras which are covering a room, and we need the data at each of those cameras, which and each of the camera can only get a portion of the room covered in the view. So we need multiple cameras or multiple sensors. So if there are multiple types of sensors, each with a different each client has a different type of sensor, so therefore the input data is partitioned across the clients. They are sensing the same phenomena, but the sensors are located differently, so that way there is a vertical split of the data. We are not going to do much on the vertical, so if you can understand A, B and C, that is good enough for today. So in A and B, there were two stages. In A, there were two stages. In B, an intermediate server was introduced. And in C, a U-shaped model was introduced so that the labels and the outputs are also with the client. So in terms of privacy, C seems to be most attractive because neither the label nor the inputs are being shared with the server. Server is only being used to offload the computations. So that is the main thing in C. Um, so again, I mean, this is the split learning without label sharing. This is the U-shaped. We get data privacy, we get scalable architecture and edge computing benefits. We reduce the computation overheads because all the computation is now offloaded to the server. But problems are, again, disparities in data distribution, and there is additional communication overhead because now I have to pass on my activations and gradients to the server. Previously, we were only doing model exchanges in federated learning, but in split learning, we have to also pass on the activations and gradients. Therefore, communication efficiency is an important aspect of this split learning performance. So, in terms of literature review, there are some traditional approaches to reduce communication overhead. For example, there are accelerating convergence strategies. There are momentum-based optimization. There is asynchronous training, which is used to make the convergence faster. And because convergence is faster, there will be less number of rounds. And because there will be less number of rounds, the communication overheads will reduce. The other strategies are about communication compression. For example, we can do sparsification, which means that only communicate a portion of the data. You may have learned of like parameter efficient tuning or LoRa or these approaches. So this is like similar to that. Or sparse models, Lasso is one example, or L1 regularization are another example. So in that context, you may have heard of sparse matrices. Basically, the update that you are giving is not like the matrix that you're sending or the vector that you're sending is not full of ones. It's not dense. Lot of entries are zero. So therefore, you can use sparsification technique to only communicate where there is an update in the vector or the matrix. And we have quantization, which means that you reduce the precision. So a floating point, which may typically take 4 bytes, now you can communicate it in 2 bytes or 1 byte, but lose the precision. And then there is pruning, where we cut down certain portion of the neural network. We don't do all the computations. Then we have model compression, where the model parameters are themselves compressed. And there's also autoencoder based compression. So these are broadly communication compression techniques. If we can compress the amount of information that goes from the between the client and the server, we can definitely reduce communication. So that is the idea in these papers. And you can find these references at the end of the slides. They are already shared in the GitHub repo. The slides and the code and everything is shared in the GitHub repo. The traditional approach to tackle heterogeneity is to enhance the federated learning algorithm, introduce the concept of adaptive learning rates, or introduce personalized learning. So these are some of the approaches. Now, what are the problems? So one problem is there is a trade-off. When we start doing communication, like compression for communication or fast convergence, it affects model accuracy. For example, in this paper where they did communication for split learning by randomized top case sparsification, there was a considerable reduction in communication, 88% reduction in communication overheads, but it had a 3% decrease in accuracy. And still, the unaddressed concern is that the computation overhead remains a critical issue, and the experimental studies in these papers lack diversity in complex tasks and realistic data sets. This is important in doing machine learning research, that we should use realistic data sets. I mean, nowadays there's lots and lots of benchmarks and data sets being released in the top conferences. And we should, kind of be up to date or look at them in doing our studies when we are evaluating our models. So the problem statement now is that we seek to achieve optimal performance, especially in non-IID settings, like someone was talking about heterogeneity in some context, and with a focus on rapid convergence, minimized computation, and communication overhead. So minimized communication overhead using our split learning setting. So now comes the main idea. It's a bit mathematical and a functional description first. I will also show it from the architecture step later. But the idea is very simple only. So we first say that deep learning model is a function f of x. You may have heard of transfer learning. In transfer learning, we kind of think of the network, we freeze certain layers of the neural network. So this FB is the back part, f of f, capital F, is the front part, and this back part is usually frozen, especially in computer vision data sets. We will say that this is like the feature encoder, and we have already learned it with like a huge amount of data. So let us freeze it and let's update only these layers. I think I said it differently. The front layers are frozen and the back layers, which are towards the output, they are kept unfrozen and they are fine tuned. So the back layers are fine tuned. The front layers are the feature encoders which work on the data. And then those features are then passed on to these back layers, which are then fine tuned because, for example, the number of classes may be different. The class that you are learning could be different. For example, if you use ImageNet pre-trained model, it was trained on the ImageNet data, like ResNet and these architectures, or MobileNet. You can get trained on the ImageNet data, but then now you have to apply it on your data like face recognition or flowers or food or whatever different agriculture data set which it was not trained on. So you can do fine tuning on those. Now in the U-shaped split, in the split learning, we further subdivide this back and the front in the client and the server. So first comes the client front layers where the input is passed, then that is passed on to the front layers of the server. Then we have the back layers of the server, and then we have the client back, and then comes the output, the value of this function on which we will compute the loss. So we introduce a caching concept and we are taking it as a key value store here. It's an in-memory store that we create. And what we do is we generate unique keys from the client data. And what we are doing is we are caching this computation. The FCF, FSF, this set of layers are doing a computation on the keys of the data, and that value is being stored. Okay, and this is because every time this data input is passed on into this network, it would be the same activation. If these were frozen, these layers, the parameters are frozen, it's the same value which would be computed every time. So this redundant, or you can say this computation which is repetitive, is being cached here, and that would later on we will see that it minimizes the computation overhead of the system. So now this FCFSF, which was being computed previously, is now replaced with just the value that is stored at the server side for the individual keys of the clients, which means the client data IDs. Now we can also do customizations at the client side. Each client may want to learn, if their data is heterogeneous or their classes are different, they may want to learn the personalized versions of the model. And for that, we have allowed for a further customization in the model that the clients can do. And then we have an aggregation step, a model aggregation, where all these customized models at the clients are being aggregated. And then there is personalized learning where we are further personalizing these custom blocks. So in the till this aggregation part, all the custom blocks have the same parameters because they are being averaged and shared with everyone. But in the personalized step, we allow each client to have its own parameters on this custom block layers. So again, as I said, this is a mathematical description, but let's look at it from the architecture layer, and I hope things will be much more clear now. So assume that this is a client. What does a client have? Client has input data. What does it want to do? It wants to learn this neural network. It wants to customize the parameters of the neural network so that it performs very well and gives it the right output. I mean, so that the loss is minimized. That is the objective function. So we have presented this for the ResNet 18 architecture. It's a system architecture now. And we are showing all the layers of the ResNet 18. There are 18 blocks. In our implementation, two of the blocks, the first convolution and the max pooling layer, are with the client. They are frozen, meaning their parameters are not updated. We took a pre-trained model, which is ResNet 18 trained on ImageNet, and we are not changing these parameters. Okay, now in the first epoch, we send the key with the activation. So we send a key and the activation pair to the server. The server passes those activation into these blocks a lot of convolution blocks in the ResNet architecture, and this is also frozen. Meaning in this part, if you send the same data again and again, same input, it will produce the exact same output. And therefore, we are caching in the very first time itself, we are caching this final activation coming out from here in the key value store. So we have a key for the client comma data ID input ID, that is the key, and the value is the activation that came out in this part. And once this has been stored, we don't need to update it. Every time, instead of passing the input, we will just send the keys to the server. The server will replace that key with the value coming from here. So this whole computation and communication will be saved. So it's a huge saving from a computation and communication perspective in our architecture. We call it efficient split learning. Okay. And then what happens? Sorry. Then from the key value store, these activations are taken up and passed through these remaining convolution and average pooling layer, which are trainable. So these parameters will update. These activations will now come back to the client back layer, and the final fully connected layer and softmax will be passed through it to generate the output. On the output, we will compute the loss, and then we'll do the gradient back propagation through these two layers and then back from up to here, because this is unfrozen or this is trainable, so only up to here. So server will also update itself, the clients will also update, and in the aggregation step the client side parameters would be averaged. Now, once the averaging is done and we get a stable model which generalizes well, we now go into the personalized phase. And here also, we just freeze the server side model. So so basically the overall architecture works like this. In every epoch, we do some computations, then the servers update their model, their local model, and then the model averaging takes place, and this happens till we come to a generalized phase where all the clients have the same exact same parameters on their back layers, the client back layers. After that, from that epoch on, every client is asynchronously in a way trying to update its own back layers so that it can be personalized to their own respective data distributions. And some clients may converge faster, some clients may take more time to converge. So therefore, they are sort of independent in a way. The data would be passed through this whole server. At this stage in the personalization phase, all the layers are frozen, only the client back is being updated, and it can use a local key value store to do personalization on its own. So when it's doing personalization on its own, we actually don't need the server anymore, and the personalization can just go on very quickly. So in the efficient split learning, we have introduced a key value store. It's a novel, contribution. It's something we have designed. My team has designed. And then we also did base model customization. We updated the ResNet 18 architecture and introduced some new blocks in it for the purpose of better customization. We have a generalization personalization model. Um, we use transfer learning. It's something which was known before. We have used U-shaped configuration. It was used before, and client model averaging server, a concept which was there before. So basically, these two are our main new contributions, technical contributions, and these are strategies that we have taken from the literature, and they address statistical heterogeneity, communication overhead, constrained resources, meaning from a computation perspective, from a convergence perspective, and as well as from privacy and security perspective. So any questions? So we have covered split learning, a few slides on them. Uh, this is the architecture that we presented. This is the functional description. So let me keep this picture and see if there are any questions from anyone. Do you understand what split learning is doing?
Participants, you can ask.
Is this at the right level? I mean, is it too advanced for you or it's too basic? I don't know. I mean, please let me know if it is too much, then I can show you some simpler stuff also. I don't know what is more useful for you.
Sir, please continue.
Okay, so now comes to the experiment part. So far, I've shown you the architecture and motivated why we are adding these components to the architecture. And now we have, like made our research objective where we have said that I want so many questions to be answered and how can I conduct or design my experiment so that I can get answers to these questions. The first question is, how does varying the number of layers in the client backside model affect the split learning performance and the computation workload for resource constrained clients? So someone may ask, okay, in this picture you have just put 2 layers here. What if I increase the number of layers? What would happen? What would be the effect on communication? What would be the effect on accuracy? And all these types of things. Second question is, how does customizing the model at the client backside affect the performance? So same thing like before I was asking on the front, number of layers, here it is customizing the layers or customizing the model. Third is, what is the overall performance of this efficient split learning approach compared to the existing algorithms for 3D, image classification and the 3D image segmentation problems. So these are the data sets on which we have evaluated ESL and compared to the other existing approaches. The fourth is this key value store approach effective? How does it mitigate overhead in terms of communication and computation compared to the other methods? And fifth, will the ESL framework demonstrate effective performance when applied to realistic medical data sets? And we are using these medical data sets which are actually collected from different hospitals across the world. And they had a lot of heterogeneity and various different characteristics, noise or even, like this, just the heterogeneity or the non-IID nature of those data sets. So there is skin lesion diagnosis where we are saying whether the skin lesion or this, like, is it cancerous? It is non-cancerous, benign. We have a diabetic retinopathy data set which is working on the fundus images taken on the eye. We have a brain 3D image segmentation for tumors. We have a kidney tumor segmentation. All of them we have evaluated in addition to some more benchmarks. So there are 6 benchmarks mentioned here. CFAR 10 and FMS are image classification. Diabetic retinopathy and ISIC, the skin one, is on the medical image classification. KIDS 19, IXI, Tiny, these are data sets used for 3D image segmentation. They have, the different number of classes. In these two, we had 10 classes. In these, we have 3 and 8. Here, we have 3 and 2. Then we are using different metrics. We are using metrics of accuracy for image classification. For medical image, we are using balanced accuracy because there are a lot of different classes and we are balancing that. For 3D image segmentation, we are using the DICE score. And the base models are also different. For these two image classification type of problems, we have used ResNet 18, which was pre-trained on the ImageNet dataset. And for the 3D segmentation, we have a NN-UNet, which is a generic model for image segmentation, especially medical image segmentation, and 3D-UNet, which is again used for the 3D data. And they were pre-trained on this data sets on pancreas and the spleen. So we have created our framework using PyTorch. Our code is available freely, it's open. Then the experiments were conducted on a workstation, with this NVIDIA RTX A6000 GPUs. And each experiment is repeated 5 times and the average is reported. So first study objective is, what is the effect of the number of layers in the client backside? So we have now created multiple splits. So the architecture is fixed, it is ResNet 18, but we can vary the splits where you exactly cut your network what portion do you give to the server, what is remaining at the client is something you can control by these splits. So in the first split, we have client back parameters only 5000 because we gave only the fully connected layer at the end to the client. Or we can split in this middle of block E when the client back would get 4.7 million parameters. This means more load on the client, this means more memory on the client, more computation required at the client. So that is the difference between these two. Here very less, here 5000, here 4.7 million. Yet another increase further, 8.3 million at the client back. Okay, but why are we doing this? Why are we increasing the layers at the client? We began with 5000, then 4.7 with 8.3. It gives more flexibility. Now you have many more layers that can be customized, personalized, so potentially your accuracy could be higher by giving larger number of parameters to the client. And yet another 9.5 million. So now we present these results. We took various splits. The smallest was RNS1 configuration, very few, only like 0.005 million parameters, and RNS4, the large split, had 9.5 million parameters at the client back. And the test accuracy, when we had 500 data points or we had 50 data points, in 500 data points hardly any change. I mean, almost the same convergence pattern looks similar. With scarce data point, when the data points are less, the slight improvement with the larger client back, but more or less it is similar. And when we are so the conclusion is, or the observation conclusion is, that when we are dealing with IID data, when we are dealing with the IIT data across clients, how we split the model and the number of trainable layers at client side doesn't matter. We can offload maximum on the server side. So this is a visual picture here. Uh, this the red with the black dots is the client back unfrozen. This represents the load at the client which the client has to compute and like take care of it. So the smaller the red black dot region would be, the lighter the model would be, the lighter in terms of communication and computation efficiency it would be better. At least in computation efficiency it would be better. Communication efficiency depends on the amount of data or the size of the vector being transferred at the split layer. Okay, and the client front is very small, so it is not even visible, very less parameters, again for computation efficiency. And the server side frozen is this yellow with the crisscrosses. The green is the part which the server is also learning. So we keep the learnable parameters the same, but increase the number of parameters learned at the client, and we find that hardly anything changed if we were in the IID setting where all clients have the same data distribution. Okay, now let's see what happens when the data distribution is non-IID. Means each client has a different data, the label distribution or the characteristics are different. Now we see that the generalized accuracy is the same, but when we go into personalization, the models with large amount of flexibility at the client side get a boost in the performance. So we had 500 data points on the CIFAR 10 data set. 10 clients were there. They had non-IID. The average accuracy was 89.33 and the standard deviation was also lower. So the variance has also reduced and the average has increased. So if we do like some kind of a statistical test, we compute p-value, we will see there is a significant improvement in the model. It is statistically significant. So the conclusion is that when we select the split, we have to be careful because by larger splits, we can improve the accuracy, but with the cost of more computation, because more trainable parameters at the client side means it has to do more computations, more updations, more memory. So that would be the trade-off. Now comes the motivation for customization of the client back. We saw that by increasing the model parameters, allows for more personalized fine-grained learning, improved performance and accuracy, but the computation load has increased. So can we customize the model and get the same performance with maximum offload on the server side? So this is the study now. So what we did is we took the ResNet architecture. This was the original architecture on the top, and we added a customized block. This is something we have introduced into the architecture and made this new architecture. Okay, what is this customized block? The customized block also we did lot of architecture exploration. We took a light linear layer, then we added another linear layer, we added a depth separable layer, we added a depth separable and a linear layer, and so many different convolution layer. So we tried lot of different customizations, different types of customizations, which varied in the number of parameters. So from the smallest to the largest, we had lot of different variations only in this block, only in the customized block. So all other blocks are taken from ResNet, no change. And what we saw is that with the depth separable layers, if you are aware of CNN architectures, depth separable were used by MobileNet. So this architecture block is taken from MobileNet, but we added it on top of ResNet here in our architecture on the client side. We see that we can get very high performance, 84% in the generalized and 88.36 in the personalized setting when we use uh, this new block. And this block has only 0.28 or 280,000 parameters. So it is much lesser than 8.39, but we are getting comparable results or sometimes even better results with adding this smaller block. So the server side load still remained the same in these two configuration, no change. In the client back, instead of splitting here and giving so many parameters to the client, I just added a small customized block which gave enough flexibility to the client to personalize in non-IID settings, heterogeneous settings, and get a huge improvement. So we have reduced number of parameters in client backend by 300x and achieved a high performance. So this is the same data. We are just highlighting the C5 configuration, which worked the best, which is the best custom block. Okay, so customization allows for high offload of parameters to server side while maintaining a good accuracy and performance. So now we compare with the existing algorithms. So ESLG and ESLP are our uh, efficient split learning generalized and personalized models. Uh, this is personalized and fair split learning. This is federated averaging. This is also one of our previous papers. So we are comparing with a previous approach of ours. Then federated averaging with transfer learning, vanilla split learning, split fed V2, which was a combination of split and federated learning, fed prox, which is an improvement over the fed averaging algorithm, scaffold transfer learning, improved federated averaging, then UNG, UNP, which are ResNet 18, unfrozen, it's a central model, then NF, GNFP, which are pre-trained weights with adjustment made to the last layer based on the dataset requirements. So there are a lot of different algorithms that we implemented for comparative study with our proposed approach. And these are the results on 4 different benchmarks. These are image classification benchmarks, so CFAR10, FMNIST, ISIC, and diabetic retinopathy. We can note that the ESL performance aligns closely with the pooled data. So this is the pooled transfer learning 89.12. It is sort of the best that one can get, which is centralized and all the data present in one place. So it aligns with pooled, and it tells that we are able to handle the non-IID scenarios, and we demonstrate 30 to 35% performance improvement over Fed average transfer learning and SLV2. So, so these are the sort of other algorithms in the literature that we are comparing with. So we are much better than the federated learning or the split learning versions. We also observe in the convergence plots that ESL has faster and smoother convergence. So these curves are for ESL, our approach, as compared to the green is with the federated averaging. When personalization begins, all loss curves slope increase significantly, indicating accelerated convergence. Unfreezing the layers UNG, UNP has resulted in slight accuracy increase for CFAR10. NFG, NFP exhibit lower accuracy, indicating that limitations of solely relying on pre-training without fine-tuning. So you do not fine-tune, just keep the pre-trained weights. Similarly, we see it for FMNIST. Here we see 16 to 19% improvement. So far, any questions? So we have discussed various experiments we did architecture, the trade-off between computation and communication. It will come later, but at least the accuracy trade-offs I have shown and the number of parameters used at the client side. Any questions so far?
Yes, please, participants, if you are having any question, then you can ask. So no questions, sir. Please continue.
So now we will show the results of the communication efficiency. So as I have told earlier that we are using a key value store. And in the key value store, we are caching the activations. So then we have a detailed calculations of all the computations that happen, all the communications that happen. And what we are showing here is that the ESL method, the overall communication that took place, it has a 37.8x reduction, our ESL method, to this previously proposed method, 86.35 to this UN method, and then 18.8 times reduction based on the federated learning, 7.5 as compared to the federated learning with transfer learning, 161.9 times reduction as compared to the split learning on the CFAR dataset. So basically, the key value store approach is even better with the personalization, and it results in huge reduction in the communication overhead. Basic idea is to cache the activation so you don't have to send the data from the client or the activations from the client to the server again and again. That is why we are getting so much reduction. And it's even better than the federated learning now with the key value store. So if we have not introduced the key value store, the split learning is worse in communication than the federated learning. But after this key value store has been added, it has become 18, 19 times, or maybe, yeah, from the traditional federated learning, 19 times reduced communication. From the transfer learning based variant of federated learning, 7.5x reduction. And if we see from the previously proposed the sparsification approaches, the sparsification approaches lead to a reduction of accuracy. For our method, we get a 13% better accuracy from the sparsification methods, and our comparison of the compressed size is also much smaller than what they are getting. And if we go for the computation reduction, again in CFAR10, we see as compared to this federated learning, we are doing 4000x reduction, meaning 4000 less times lesser computation, which is like many orders of magnitude better. So this paper, where I'm presenting it from, is been accepted in the IoT journal, which is like one of the top journals in IEEE. So we got like very good reviews and on this work. So then comes this skin lesion dataset. So this dataset had natural splits. It was collected at 6 different hospitals in, I think, in different parts of the world. There's like many of them from Spain and Vienna, Austria. I don't know these two, but they are different hospitals in Europe. And there's a high quality dermoscopy images of the skin lesions. There are limited clients, so we are doing a cross silo setting. So these are 6 different hospitals. There is heterogeneity between clients, there is high label imbalance, this is a multi-class classification. So this is like a UMAP plot of the data showing the various, different clients having their different distribution. So some clients have more of this distribution, the blue is spread over here. So there's like a lot of heterogeneity in the feature space, you can see. Uh, Now, what did we do? We used a balanced accuracy matrix which accounts for both positive and negative outcome classes and doesn't mislead with imbalanced data. We used a weighted focal loss, which kind of applies a modulating term to the cross entropy loss. So you might be familiar with cross entropy loss. We added this alpha t and this gamma. So this is a function. And this shows the data distribution among the clients. The larger circle shows more training samples. So these are the 6 clients, the same as this picture. But now you can see clearly that client 1 is so many more class 0 example, but client 2 has very less. Class 1, 2 are 0, 1, 2 are more in client 1, but in client 2, 0 and 2 are very less. Right? So you can see for each of the class, different clients have different number of samples. So this means the training distribution is different. Even in the feature space, there is difference. So both in counts as well in the feature distribution. And here we see that our method, this ESLP, the personalized approach, achieves a balanced accuracy of 71.4%. So, which is like a major improvement over the federated learning. Um, and yeah, mainly it is about this performance improvement that we have shown. From the convergence also, we see the faster convergence. The effect, this red line is when the personalization starts, and we see the accuracy jumps because of personalization here. Then we have the diabetic retinopathy study. Um, Here also we see, major improvement over federated learning. Then we can also see the evaluation of the key value store. Um, Even in these realistic data sets, from the real world ISIC DR, we see a huge reduction in the communication overhead as compared to these previous approaches. So communication overhead, although there is a variable, like in ISIC, it is only 2x reduction, but in certain data sets, we see even more. But computation reduction is huge. I mean, especially this is very relevant for IoT devices. The traditional vanilla federated learning, if you use it, it would be like very computation intensive. But here we have seen thousands of time reduction as compared to the federated learning approaches when we use the split learning. So this is the main takeaway. We got like, so now, okay, with the image segmentation, things are a bit more difficult, especially in the 3D scenario, because in segmentation problems, the communication overhead is difficult to reduce. So this is an example. When you get an MRI like this, we want to segment the brain image, and suppose this was the target and this is like the prediction. So we are trying to segment a region uh, of the brain and estimate its volume, let's say, and this is the target, this is the ground truth, and this is what the model is predicting. So it's a brain segmentation problem, and there are 3 different hospitals. There is a different ratios of males and females. There's this age distribution is also slightly different. So this is the demographics for this Fed IXI tiny data set. Here we are using the dice score, and we are using this dice loss here. So this is just a visualization. So suppose this was the mask that was made by the computer or by the model, and this was the ground truth. So the higher the intersection is, the better your dice score would be. And in the in the denominator, so the numerator we have 2 times the true positives, and the denominator we have 2 times true positive plus false positive plus false negative plus some epsilon to ensure numerical stability. So this is sort of the die score, and if die score is good, basically it will mean that your predictions are close to the ground truth mask. So now in these segmentation architectures, it is based on UNet, and UNet again is sort of visualized here. We have some layers in the image, no, in the ResNet, what we have seen is that the communication, the output is only of vector of size 10 if it's a 10 class problem, right? But in UNet, the output is a mask and the size of the mask is of the same size as the input image. So because of that, at the end, you have to generate a large size output. Therefore, the communication actually increases in these back layers. So when we apply split learning to such 3D segmentation problems, it becomes very difficult to decide where to split such models. Okay, so we may reduce computation of overload by keeping these layers at the server side. But when we split in these layers, the communication that is going on through these layers is very high. So that causes a huge communication overhead. So this is some visualization. We may give these 3 layers as client front and say these 3 layers are client back. This is sort of one type of split. So keeping the front the same, see how I'm moving this split from here to here. Okay, so this is my split 2. Again, I can split here. This would be my split 3. This is my split 4. So now I'm showing you what are the various options. So in split 1 till convergence, I have sent so much data like 7.9 gigs, 7.9, 2.5 gigs. This is less than a gig, 926 megabytes. So this is the amount of data sent, and this is in terms of the number of floating point operations, which is the computation load. So in the previous image classification cases, when I was getting low communication, I was also having low computation overhead. But here one split is better in terms of computation efficiency and another split is better in terms of communication efficiency. So this is sort of the unique problem that we saw, and also the die score was based on this some intermediate split like split 4. uh, so what we are trying to conclude here is that the optimal or the best split depends on the resource constraint. If your IoT device is very constrained on computation but communication is okay, then you can go with split 1. But if it is constrained on communication and computation resources are okay, then you can go with this one. Or if you have like a trade-off, you can assign a cost alpha and beta to computation and communication, and depending on the value of alpha and beta, you can choose which of the split minimizes your objective function. So very interesting studies can be done in this 3D segmentation, and you can determine what is the optimal choice. Similarly, we have worked on the kidney tumor segmentation dataset. Again, it was collected from 6 different hospitals. This is a visualization of the ground truth. I mean, this is like the scan, and then you have segmented out the kidney, both the kidney and the tumor. So there are 3 classes. So there is a background which is class 0. The pink are like say the kidneys, and then within the kidney there is a tumor. So these are the labels in this data set. Again, we have the various splits that we have considered. So split 1, split 2, split 3, split 4, split 5, and what we find here is split 3 gave us the best result. There is this total data in terms of communication. Split 4 was the lowest in terms of communication. Split 1 was the lowest in terms of the computation, and you can see this is like huge, 167,000 gigaflops. Okay, I mean, like our processors are gigahertz, so we can do in 1 second 1 gigaflop sort of, I mean, or few gigaflops. So it will take these many seconds. So basically convergence will take a long time. You know, these are complex models, so it will take a lot of computation resources. We were able to do these experiments on GPUs, but if you just put it on CPU or some of these, like, processors on IoT devices, it would be very challenging to do this. This is the overall performance. The ESL performs like 45% improvement as compared to the Fed average, the standard Fed averaging algorithm. There is communication reduction here as well. Only in the IXI tiny, in this part we are not doing reduction. The communication is 5 times more actually. So we are not always best as compared to the Fed averaging for the 3D segmentation as well as the amount of communication that takes place. But computation reduction is significant and that can offset the extra communication. So conclusion is that the split learning is feasible and effective within the federated domains. It is well suited for edge computing applications, enables this on-device model training. We can achieve optimal performance with the customized models. We can reduce computation overhead. By careful configuration, we can reduce both communication and computation overheads without reduction model accuracy. Its applicability extends to domains like natural language processing. Currently, we are looking at LLMs, how to split LLMs and stuff like that. In future work, we are looking at support for heterogeneous devices as well, dynamic model selection customization. We are actively working on support for out of order distributions where at test time the distribution changes, secure aggregation techniques, real world deployments with actual test beds with IoT devices, and new architectures for split learning. These are the references that have been used. These slides are shared in the GitHub repo. So now we will answer any questions and then maybe take some 5-10 minutes break and then go through the code, both the federated and split learning code through our code repo. So that is what is left now. So let me know if there are
Yes,
any
please,
questions.
participant, please put your questions in chat box or you can unmute yourself and ask the questions. Yes, please. If you are having any question, then you can ask. So I think there is no question from participant side, sir. So we can take a 5-minute break, then we can continue. Gagan, sir?
Okay. Okay, so we are taking a 5-minute break. Okay.
Oh, okay, sir. Oh.
Hello. Can we give the presentation rights to Manisha?
Okay, sir. Okay, sir. Just a minute. I'm simply providing that.
Okay, okay. So we'll encourage everyone to go through the code along with us. If you have a laptop or a computer, you can execute it. I mean, it's all executable. Uh, so that way you can get better understanding of the concepts.
Excuse me, sir. So,
Yeah.
what is complete name of Manisha? Manisha Chawla or something
Yes,
else?
Manisha Chawla.
Okay, okay.
Manisha, are you there?
Yes, sir.
Okay. Yes.
Yes, ma'am. Now you are having the control. Now you can share your screen.
So please confirm if the screen is
Yes, ma'am.
visible.
Your screen is visible.
Thank you. So good evening, everyone. My name is Manisha Chawla. I did my MTech from IIT Bhilai under the supervision or guidance of Dr. Gagan Raj Gupta sir. And today I'll be assisting you through hands-on demonstration on federated learning. So I think there are two concepts that we have learned so far. First is federated learning and second one is split learning. So this a notebook that is available on your screen is on federated learning. So this is available on the GitHub repo, that is link is already shared. I think this is on chat. You can get the repository from there. This. So if you have laptop and you are executing the code with us, so you can follow these instructions. These instructions are also there in the GitHub repository. You can go through that. So shall we start with the code or maybe we'll wait?
Yes, ma'am. You can proceed.
Okay, thank you. So in this particular repository, we'll see federated learning on a very simple data set, CFAR10, using ResNet 18 model. So here we'll do data preparation, we'll do client-side training, model aggregation, and evaluation. So first of all, we'll see what is federated learning. I'll repeat it again. It is already there in the slide, but again. So so federated learning allows multiple data owners to cooperate in training a global model without exposing their individual data sets. So I think this is more clear from this picture. Suppose there are multiple clients or data owners and they want to train a model and they have limited data and they don't want to share their data. So a solution for this particular problem is federated learning. This solution is given by Google. So suppose you want to train, now you have your own data, you train the model based on your own data. Now you share the model with the server. All clients will share their model. The server will get multiple models from different clients. Server will aggregate those models and give it back to the clients. Then the client will again perform training until we'll get a global model, which is generalized model. So we'll see these approach through a simple code here. So we have divided the code into multiple modules. So first we'll import all the dependencies. Here we are using PyTorch. So PyTorch is a library which provides all the necessary functionalities for tensor operations and model building. So we'll import all the libraries. Now the first function which we have used to define and transform the data set. So here we have used CFAR 10 data set. So I'll first go through what is CFAR 10 here. This data set consists of 60,000 images. You can see the classes here. There are 10 classes. So there are 60,000 images. The size of each image is 32 cross 32. So per class, there are 6,000 images, out of which 5,000 images are for training purpose and 1,000 is for testing purpose. So this data set is available here in PyTorch library. We can directly download this and use this data set. So this function here you can check the line, this line and the second one. Here we are downloading the dataset, train and test dataset. Now you can see this transformation. So here we are performing transformation like resizing, converting it to tensor, and then normalizing the dataset. So as I already mentioned here, images are of 32 cross 32 size, and we are resizing it to 224 cross 224. So why we are doing this resizing, we'll see later in the code. So this function will return training dataset and test dataset. After that, there is second function, second module, which we'll use to define the model. So here we are using ResNet 18 model. ResNet 18 is a convolutional neural network. You can see here the model architecture. There are 18 layers, and this model, this particular model is convolutional neural network, and we have used pre-trained version of it, meaning we have used the model which is already trained on different data set, which is ImageNet, and we'll use this model directly here. So you can see the code line number 1 here is to get the pre-trained version of ResNet 18. Now, because we are using transfer learning or pre-trained weight, so we need to set this required grade to false, meaning we don't change the weight. Now, because this ResNet 18 is trained on ImageNet, where the input size is 224 cross 224, and output will be 1,000 here because there are 1,000 different categories. So but in CFAR 10 we have only 10 classes, so we need to change this last layer. Here with this line we are changing the last layer, where the input features or input activation size will be the same, but the output will be of 10 here, which is the number of classes. We have set it to 10 because again CFAR 10 has 10 classes. So this function will give you the model. Now, because your input size, image size is 224 cross 224, so this is why we are resizing the image of CFAR 10 to 224 cross 224. Now the the third function is train a single client. So here this particular module or function will train a client. So you can check we are calling the get model function to get the model. Then we are defining the loss function. Here we are using cross entropy loss and the optimizer to train the model. Now the training starts here. We have set the epoch value. You can set it to whatever value you want, or you can set any convergence criteria here. With the help of this loop, we are training the whole model for a single client, and then we are returning the model. Now we have next function where we are saving the model weights. So now you have trained the model. This function will save the model weights. Next one is to aggregate weights. So in federated learning, as we notice that the server gets the model from different client and then aggregate those models. So this function is for that purpose. It gets the model from different client and return the aggregate model. Now the next function is evaluate model. Now that you have trained your model, you have to evaluate on test data. So this function will evaluate the model on test data and return the accuracy. So here the metric that we have used is accuracy. Now you have all the functions ready with you. We need to just put into a one function, that is main function. So here we are calling all the functions defined above and perform the whole training. So first we'll get the data set. It will return the training and test data set. We'll define the number of clients here. So here we have set it to 5. Number of samples per client. So because we have used CFAR and there are 60,000 images, out of which 50,000 images are for training purpose. So out of those 50,000, we are giving 5,000 images to each client. So this is actually a simulation of federated learning. We don't have clients at different location with their own data. We are using a data set and dividing the data set to give effect of simulation here. So now we have defined the number of epochs to 5. You can change these values. Now with this loop, we will train each client and then aggregate the model, and we'll see the performance of individual client model and aggregated global model. So here we have used this random function to generate random samples for each client, and then we'll give those 500s to the client. Then we define the data loader for that particular client. You can set the batch size here. So we have set it to 32. Now we call the train client function to train that particular client with the train loader part and the number of epochs that you have set earlier. So this function will return the model. Then we append and create a list of model and pass this list to aggregate function to aggregate that model. So we'll save the individual model, we'll save the aggregate model, and we'll perform training again and again until we get the generalized model, like best model. So now that we have trained all clients and we have got the aggregated model, now we'll check the performance of the model based on the test images. So the test data is unseen data. We have not used those for training purpose. Now we'll check the performance. So after running this particular set of lines, this particular cell, you will get the output. You can check. So client 1, epoch 1, the loss value. Again, client 1, epoch 2, loss value. So we have used 5 epochs. You can see the loss value is decreasing. Now again for client 2, 5 epoch, client 3, 5 epoch, and so on. So there are 5 clients. After getting different models from all those 5 clients, we'll aggregate and save. Now that you can check here, we have performed testing on aggregated model and we are getting 70% accuracy. Now, if we just test individual model of a particular client, like not the aggregated one, the local model of a client. So we are getting accuracies 58, 58, 58, 64, and 60. So with the help of this particular example, we can say that this aggregated model is generalized over all the clients or all the data set from different clients. So it is better than this particular local model of a client. So this is all about this code. If you have any doubt, you can ask or you can run the code. So I would request you, if you have laptop and you are going through the code, you can change this value number of clients. You can change this value number of samples per client and this value number of epoch and rerun the code and check the values here.
Participant, if you are having any doubt till now, then you can ask. And please continue.
So this is like code for federated learning. So sir, shall we move to split learning code or we'll just...
Ma'am, you can go with your flow.
Okay. So now we'll move to split learning part. So similarly, this particular notebook we have developed for split learning. This code is the simpler version or simulation of split learning. So first of all, we'll see what is split learning. So suppose in federated setting, suppose a particular client is having limited resource. Now you have to train the model over this particular client on the machine. So you can't run the whole model here. So for this resource constraint issue, we shift to split learning, because in split learning we will split the model. So we'll give some part of the model to the client and offload other part of the model to the server. So here are the 4 variations of split learning. In the first case, the client and the server. So there are 2 splits only. First few layers you give to the client and the last rest layers you give to the server. So, but in this setting, you can check that the output is with the server. So we need to share the output with server. The second setting where there is another server that is called intermediate server. Again, but here the split is, there are only 2 split. Now, the particular setting that we have used for our code is this third one, where we divide the model into 3 parts. So first few layers with the client. Now the intermediate layers are with the server, and the last few layers are with the client again. So in this particular setting, we don't need to share the labels with the server. So this is like more secure version. And the last one is this, where we give like few layers to the client and rest to the server. But here each client is having few features of the whole data set. Like suppose there are X number of features. So n number of features. So X will give to the first client and n minus X to the other. So in this particular code, I have shown this third version where we split the model into 3 parts. And this is what we have used for ESL also. So again, we'll go through the code. We will import all the dependencies. We have used PyTorch here. So now here also we have defined multiple functions for different purpose to perform different tasks. So first one is to get the data set. Again, this will here also we are using CFAR10 data set. So we are using same transform function and same code as we used in federated learning version. So this function will return train loader and test loader. Now we'll define and split the model and define the model. So because we are using this particular version, so there are 3 parts. First one, we are calling it as client front part, the server part, and the client back part. So client front model, server model, and client back model. So we have ResNet 18 and we are dividing it into 3 parts. So you can check here. This is the ResNet 18 model with 18 layers. Now how we are defining or how we are splitting. So you can check this particular image. So the first 2 layers, convolution and max pool layer, we give it to the client front model, and then all layers will give to the server except the last one. The last one will give to the client back part. So this is how we are using this split setup. Now you can check the code here. So in ResNet pre-trained version, we are giving few layers, like you can set this client front layer value to whatever value you want. So we have set it to 1 here. We are giving only 1 layer to client front model. Now from client front model to the number of layers that you want to give it to the server, you can set it to, again, you can change the split and set different values. And the last client back model from this server layer to client back layers. So you can create different split by passing different values of this client front layer, server layer, and client back layer. So this function will return 3 different models or 3 split, like client front, server model, and client back model. After this function, we have defined another function to train the client back part. So now in this particular notebook, to run this code faster, I am only training the client back part, not the client front and server part. So if you run the code, you will get the result within 5 to 10 minutes. But ideally, this server part, a part of server model, we need to train, like we need to fine tune the model. So you can change the code based on your need. Now here we are passing the input to client front model. So after this particular process, you will get some output, which we are calling it as intermediate output. We are passing those intermediate output to the server. Now again, we'll get some output from this server model, and then we'll pass those output, like server output, to the client back to get the final output. So this final output will be the prediction. Now, this particular code will train a client. After training, again, we need to perform aggregation. So here, because we are training only the client back part, so we are aggregating that part only. Because we are freezing client front and server, so it will be the same. So we don't need to aggregate that part. Now, the next one is to evaluate the split model. Again, evaluation means testing. So we'll test the model on test data. So here we are using accuracy as a metric. Again, we need to call all the functions to run the split learning code here. So first we'll call the get dataset function. Then we'll split the model and we'll get client front, server, and client back model. We are defining number of clients and number of epoch per client. Now we'll instantiate the models like client front, server, and client back for all the clients. We'll set the criteria, means the loss function. We are using cross entropy loss. Again, we'll divide the data set and give the samples to the clients. So here we are passing number of samples. So you can change the value of this particular variable. Here we have set it to 500. So each client will get 500 samples. Again, the train loader part for all clients. Then we'll define the optimizer. And then we'll call the client back, train client back function that we have already discussed. So this function will return the model. After getting the model, we'll pass all the models and call the average function. So we'll aggregate all the models. After aggregating, we'll test the aggregated model and the individual local model for all clients. So again, you will see here the log values. So client 1 accuracy is 66, client 2 is 70, and likewise we are getting 76, 68, and 76. But the aggregate model accuracy is 78%. So this is the code for split learning. You can see the difference between this split and federated learning. So if you have any doubt, you can ask.
Yes, please, participants, if you are having any doubt till now, then you can ask.
So like this hands-on was mainly designed to get the essence of this federated and split version. So this is the simple code. Actually, the code that we use for the ESL paper is different. So there is another GitHub repository for that. I would recommend you all to please go through the notebook and code part. And if you can run the code, please try running it with different value, like different number of clients and number of epochs and number of samples per client.
Okay, so anybody having any doubt or confusion, then you can ask, please. Make the session interactive.
Even if you have any doubt, like how to run this code, where to run this code, like I can help you. Sir, these two notebooks that we prepared for this particular session.
Okay, ma'am. Okay, okay. So this is all from your side?
Yes.
Okay, okay then. Thank you. If you are participants, if you are having any doubt, then you can ask. Gagan sir, if you want to say something, then we can.
So yeah, I mean, I just would like to kind of give the overall picture. I mean, like say machine learning means we have to learn from data and we are performing certain tasks. It could be a classification. I talked about 3D segmentation. It could be prediction. So all these are different types of tasks where we are learning some models from the data. And what we discussed today was that the data itself is generated at various places. It is distributed. So it is could be user data or some client's data, device data, could be IoT devices. So we discussed how we can train the model in a distributed way where the data is generated from multiple clients and then the models are also being updated by the clients. So in federated learning, they are updating the complete model. In split learning, they are updating portions of the model, which we have split and given to the client. And the whole research is about how to customize those models, how to personalize those models, how to get efficiency in terms of reduction of communication messages and reduction of the amount of computation we have to do. So what we have presented is in the form of these slides. So first you should try to understand what is machine learning, then you have to understand what is deep learning, then you can go to federated learning, and then split learning is like our research. That is where we have developed these new algorithms for efficient federated learning on the IoT devices. So how can split learning be integrated with yes? So in edge and cloud computing architectures, what you can think of is the server layer is in the cloud and the edge is where our clients are. So edge devices will be collecting the data and they would be updating the model right there. And the part of the model computation is offloaded to the cloud. So whenever I am saying, let me just share the screen and give you that perspective. So whenever we are saying that we are running these things on the server, that is basically can be said that this server is in the cloud. So all this data that is being sent by the client is being sent to that cloud server. Let me go to an initial diagram which is more clear. Let's say this one. So this server layer can be implemented in the cloud. And these clients which are there, I don't know where there is multiple client picture. Maybe like these are different clients, these are the edge devices, this is the server. Server is in the cloud. We have to minimize the communication that is going between the edge and the cloud. That is one objective. We have to minimize the computation that we are using at the edge devices. That is another objective. We have to get scalability on these servers. That is what we can get from the cloud. So actually we are showing it one servers, but it could be a pool of servers which are serving these clients. So that can also be done. Does that answer your question? I mean, it is can be very easily applied. In what scenarios might split learning outperform federated learning? So we have shown a lot of benchmarks. In this talk, we showed you various benchmarks from the medical setting. That's ISIC DR is diabetic retinopathy, skin cancer imaging. So here we have shown that the ESL method can outperform federated learning by 16%, 19%. I mean, like a huge improvement over the federated averaging methods. As well as we are getting high reduction in the communication as well as in the computation, like thousands of times reduction. Uh, So in smart homes, yes. So basically, I mean, in smart homes, we have to do predictions, right? Like, let's say when to turn on the heat or when to turn on the cooling. or like this face recognition which I was saying. Can you recognize at the door that this is a known visitor, a family member, a friend, and then the door can open when those people come, or when some stranger comes it can, or even when the known person comes you can welcome them by their name. So this is like a face recognition application. So you can have a camera, the camera recognizes the face, and then it plays the message, it announces to you or sends you a message that this person has arrived or this person has left the house. So those are image type of problems. The IoT application, now you don't want your friends' data, your known people data to be released to these companies or to the central server. So the cloud provider will not get any of the photos or the images from your home. All the recognition of the person is being done through a model which is at the home itself. So therefore you have privacy. It doesn't compromise your data privacy, yet you are able to build these types of applications. Now you have very limited data, so if you build this application just with your data, it may not be perfectly accurate. When multiple such IoT devices are collaborating to learn this model, the face recognition model or whatever, it can be much more accurate. Because in the real world you have to deal with various lighting conditions and different noise occlusion that you will not be able to learn by yourself with your limited data. But when these multiple IoT devices collaborate to learn these models in various conditions, you will benefit. And your local model which is running in the IoT device doing this face recognition for your smart home, that will work much better. That is what we have demonstrated. You can plug in your data set into our code, both the simple code that we have shared in our GitHub as well as our paper repository. You can do the experiments and see what are the results you're getting. Any other question or discussion?
If participants, if you are having any other question, then you can put in chat box,
Yeah, in
or you
general
can
also, if you
unmute
want to
yourself and
ask
ask.
any question. In general also, if you want to ask anything, we can answer. We have some time.
So there is one more question in chat box.
What are the primary advantages of using split learning in IoT devices over traditional centralized? So to summarize, the primary advantage is that the split learning, mainly the first very important advantage is that it reduces the computation overhead, because in split learning all this computation is now offloaded to the server. So this huge reduction, I mean the 1,000 time reduction is not less, it's huge orders of magnitude reduction. It can also translate into the time it takes to run the models. So that the heating, the battery it saves on the device, all of that are related to this. So therefore, it's a major benefit. It's the first important benefit, that we get huge reduction in the computation while doing this deep learning on the clients, both in terms of learning the models as well as in inference also you get some benefit. And then we also showed that it is good in terms of communication after we implemented the key value store. So that is the ESL, the efficient split learning, as well as in accuracy, we are better than federated learning. So in that sense, across all metrics, we were able to show good results. And then how does split learning address privacy and resource constraints? So it addressed privacy because the both the data as well as the labels were residing with the clients. We did not share our data with anyone in this architecture that we had shown you. All the data resides still at the client only. The data, the local data is at the client, the labels are at the client, so nothing is shared. uh, like in this architecture, input data is with the client, label is also with the client, so nothing is shared with the server. In that sense, you're not revealing your data or not sharing over the internet or not sharing your raw data with anyone. So that sense it is solving the privacy aspects. Resource constraint I already said, Resource constraints, we reduce the computation overhead by several orders of magnitude. So that is the main constraint. The IoT device have limited battery, limited power, limited energy. We want the computation to be less on them. Lightweight models are needed. So split learning basically gives you the accuracy of the state of the art deep learning models, but from a load perspective, it's only 5,000, 10,000, 20,000 parameters that you have to train on the client. So it appears like a very small, lightweight model from a client perspective. So it gives you sort of the best of both worlds as far as image classification is concerned. The 3D segmentation is a more difficult problem. I don't think it can be done on the traditional IoT devices, but like you can get edge devices from NVIDIA. They have some, like boards, Jetson Nano, for example. Jetson Nano board is very capable. It can run deep learning models on the edge. We have also tried these on RPi, Arduino. Very small model of split learning can be done even on a Arduino. So it is possible to run deep learning models on these small devices if we do the right customizations and this kind of a split learning implementation. So this is one of our ongoing work that we want to implement or execute these split learning code on these traditional or some of these upcomings like this Jetson Nano, as I told. It's also old now, but it's a GPU type of GPU based device. RPi is a device which can easily run split learning code. So few online research resources. I mean, if you go to my webpage and some of my courses are linked, my machine learning course is linked, deep learning course is linked. So you can find lot of references for online materials in those. Um how does the split point affect the computational load? So this is where we did a lot of experiments to show that the split point actually matters. And we saw these trade-offs with the various splits. So like this split is the thinnest split. The client has only 5,000 parameters. Then we go to a 4.7 million, 8.3, 9.5. As long as the data is IID, your train and the test is all IID, it doesn't matter. So in the terms of accuracy, you'll get similar accuracy, but the client load would be more if the parameters are more. So we recommend using a thinnest split. Our conclusion from all these experiments is use a very, very thin split for doing your implementations, which will keep your IoT devices very less load. You'll get high accuracy as far as IID is concerned. And when non-IID is there, the new innovation is that you can add a customized block to this pre-trained architecture. This is a block on which you are learning the parameters, updating the parameters. But even if it's a small block, I mean, with only one depth separable layer that we added with 280,000 parameters, it achieves the same performance as a very large 8.39 million block. So this is sort of the major, I would say, innovation, that by customizing the block that is there at the client, adding it, we can achieve much higher performance. So there are a lot of experiments in the paper. You can like read it. Manisha, please also like add the link to the paper uh, and our main GitHub and put it on the chat. Then how
Sure,
to
sir.
overcome limited availability of pre-trained split models. Yes, so that is good. um, we will usually get the pre-trained deep learning models. They are not split using our code, like the code repo that Manisha will post here. Um, we have given certain splits already in our repo, so you can see how the split learning is done, as in like how the models can be split. That you can learn from our code. And what you have to do is, the pre-trained complete model is there, you have split, use the same parameters entirely, and then in the last few layers is where the training is happening at the client and as all the server side, that you will see in our code. So that way, even if pre-trained split learning model is not there, you can work with the usual pre-trained deep learning model, the full model, learn how to split it, reuse the same parameters to begin with, like the pre-trained model, and do the fine tuning both on the client side and the server side to get your best results. Explain step by step how you would set up a split learning. So that on a RPi device. So what we have shown here today is a Colab file where we have done split learning on, like the Colab, and Colab has one TPU on which it runs. I mean, the same code will also run on CPU. So for this, we'll have to create an environment where and we have that code. Actually, we have a client server code. The one which we showed today is a simulator where the clients and servers are simulated in the same code. For this one, basically RPi will be the IoT device. It will run only the code of the client, and we will have to set up another server either on the cloud or on a workstation, and then we can show the communication between the client and the server and how the split learning framework works. So this is a very good comment. I mean, this is something we will add to our GitHub repo. An example of how to set up a RPi device using the split learning, or maybe a couple of devices, so that like the researchers or practitioners in this field can learn how to use the split learning, maybe even for small simple data sets like you've said MNIST, but actually we can do CFAR and even some other complex data sets on a RPi. So this we don't have a ready demo yet, Mr. Nagarajan. We will work on it. It's a good feedback. What prerequisites? So mostly we are using PyTorch libraries for simulation. Once we go for the IoT devices, there are some more libraries that we would need in these devices. And what those exact libraries are, we'll have to like kind of, do it first and then like confirm what all is needed. There is TensorFlow Lite, there is a PyTorch edge distributed sort of version. So there are libraries of deep learning which are available for IoT devices. We just need to kind of test it, and then uh, we will post it on our GitHub. So if you watch our GitHub page, I mean, you will see some updates in the future. Thank you for all these questions.
Any
Anyone
other
else?
question, participant, please? Okay, so Arvind sir, over to you.
So Gagan sir, thank you so much, and Manisha, thank you so much for your generosity and for inspiring us with your knowledge and passion. So much.
Okay, thank you.
Okay, most
Thank
welcome,
Bye.
sir.
Bye bye. Good evening.
Have a good night.
Good night.
Okay, bye.
Bye.
Okay, so thank you everyone. That's all for the day. We will join again tomorrow for around 2 o'clock for upcoming session. Thank you everyone. Good night.